So hello and welcome back to my C++ tutorial playlist. This video will be a little bit longer than usual. So far we didn't code too much yet, and I feel like I should cover a lot of the syntax that C++ uses. So I will use this video to give you a quick rundown of the most important C++ syntax and features there are. So you will be able to code in C++ after this video and also be able to read most C++ code. This basically is a quick boot camp. This video is not as structured as some of the other videos that will come and did come so far. I only have a reference list of all the topics I want to cover. First of all, this is the code that we left off with last time, and I want to clean it up a little bit. For example, we don't need to have the module. Also, we don't want to have anything in our main. We will build up from here step by step. Also, I want to adjust our CMakeList. We only want to include the main CPP here, and that's it. Also, I want to specify some flags that are good, especially if you're starting out, to get used to safe coding practices. And the first flag I want to specify is error. This basically means that any warning will be treated as an error. Then we want to have all warnings enabled. And this is a little bit misguiding because all doesn't really mean every warning, but only the most common warnings. We also want to have extra warnings, and we also want to have the conversion warning, which warns us about implicit type conversions and narrowing type conversions, and I think also shadow. Let's see if it compiles at all. Right now, as it is, we only have an empty program, so it should be fine. And as we can see, our program does run so far, so that's a good starting point. So let's switch over to main. So let's start out here. The first thing that I would like to cover is basic input and output operations. And as we've seen previously, we can use print or std print line to print something to the console. And we can use placeholders in here, like that. The same applies here, only that we print a new line here, then also at the end. And to use print, we do need to include the print header. But what you most commonly see nowadays still is cout, and then we have this operator to forward something into that stream. And to make use of this functionality, we need to include the header IO stream like this. So if we would build this and then run the application, so you can see that only one hello world gets printed, and also that it doesn't add a new line at the end, so it doesn't break. Also, we don't know which one printed, so let's change it a little bit. And also, let's add the new line at the end. Or we can either use this new line character, or of course we can also use print line. And likewise, we can add the new line at the end here. So let's save it. So what might happen here, that we don't see both prints. This might actually happen if we exit the application unexpectedly with an error or exception. Then we need to flush the console because it doesn't do that automatically. And one way to do that is to use the end line. That puts an new line character at the end, but also flushes the console. So the buffer that C++ holds internally will get flushed and will put on the screen immediately. For debugging, I also like to disable the buffering of the cout stream entirely. And to do that, we can use this. And of course, to enable it again, we can unset the same flag again, because it of course has a reason that C++ buffers the characters that we want to send to the screen. And that of course is performance. Any system call we do, so we interact with the operating system, that costs time. And to minimize that, we can buffer all the characters we want to send to the screen and basically batch all the output operations we want to do into a single one. So we only need to ask the operating system once to print something. And that is, of course, more efficient. But let's remove this for now. You should now be able to print something on the screen with ease. So the next thing I want to cover are variables and data types. So what we've seen so far is we create a variable, let's say integer a, and assign it a value of 42. So what this line means, we create a variable called a, which is basically a box with a label on it called a, and integer is the type of the variable. A type annotates how big the variable is, how much storage it has, and also the shape of the variable, so the meaning the value inside of that box holds. And here we initialize it with 42, which is basically just a number we put inside the box. There is a small difference between writing this and writing this. The first assignment here is not really an assignment, but an initialization. So we do already create the box with 42 inside of it. And what I like to do to differentiate those two better is to use an initializer list like this. So we now know, okay, this is an initialization and this is an assignment. Here we move a value into an existing variable. Here we create a new variable with the contents of 42. It now also complains that we don't use a. This is fine, but of course if we would like to get rid of that warning, we can cast it to void with an annotation that we want to do something with it later. Or there's also the possibility that we annotate the variable with maybe unused. Both of these cases should of course be exceptions, and usually we want to have the warning that the variable is not in use and we can get rid of it because we don't use it anywhere. There are different built-in types into C++. For example, integer here stands for a whole number. So let's start with float first, maybe. And that might be something like this. Also, what you can see here is that we have to annotate the f here at the end. To annotate that it's a floating point literal. We don't do it, then C++ will use a double, as we can see here. And a double is also just a floating point number, but with double the precision of that. And we can store really precise numbers here. Something like that. We can of course also, to go more into depth here, an integer is a signed number. If you want to only store positive integers, there's also the unsigned, like this. And there are a lot of other types that can store numbers, but let's move on to some other types that have a little bit of a different meaning. For example, we do have a character, and we can store characters or letters in here. And if we want to store multiple letters, so a string, we usually use the std string. And notice here that we don't use this initializer list here, but this is a constructor call because string is a class. And this literal here, as we can see here, this is not a string literal. This is a const char of the size 6 by 6 and not 5, because we also implicitly store a null terminator at the end that basically indicates when the string or this character array is over. And we can pass that into the constructor of the string to create a string. And to use a string, we also need to include the string header like that. What's really important is that we have Boolean values, and they only can store true or false. These are the only two possibilities here. And with them, we can basically branch our program later. If something is true, then we go one way, or if something is wrong, then we go the other way. For now, to don't get compiler errors, I want to annotate all of these variables with maybe unused. This looks very ugly, and we shouldn't ever have to do that in real code. This is just so it doesn't give us any errors here when we don't use these variables. I think that's already the very most important types that we use every day. But of course there are many more, but you should now get the gist of it. There are types that can store numbers, characters, or a single character. And there are custom types like the string that have custom logic. This is not really a custom type because it comes from the C++ standard, but we need to include that class from this string header. And we will see later on in this video how we can define our own types or classes. And then booleans, which can only store true or false. What is important to notice here is that we can change all of these variables. If we want to assign letter to B, we can. And then later on the program, when the name letter is used, it will look inside of that box and find the character B and not A anymore. In C++ or in any programming language, it's really much like a cooking recipe. You go from the top to the bottom, step by step, line by line. And this changing of a variable leads us to our next topic that I want to cover, which are constants. And sometimes we don't want to change variables because they are, as the keyword const implies, constant. So we only want to initialize them once and never change them again afterwards. How do we name this? Well, let's use C, something like this. And then when we try to change it later, then we can't. Something like this can be evaluated at compile time already. It doesn't rely on user input or any dynamic data, so we can even be more strict and make this a constant expression. This will then tell the compiler this can be evaluated at compile time, and we don't need any runtime information to calculate this value. But for anything that relies on maybe user input, we can still use const like this. Something like this. So we can read in something from the user with the cin stream, and we specify where we want to store that value that we read in. Here it is in the variable user input. Then we can later on use that user input to initialize a constant value of d, and then we can print out d to the console again. These are already the very basics of constants. Of course, there is a lot more, but we will go into more depth in the future in this playlist. Then, as I already spoiled, we can branch off our program with control structures. And the most basic one is an if statement. We can check our is wrong here and execute some code conditionally here if is wrong was true. Like this, maybe. Then we also can have an else block. Like this. Both of these expressions only execute the next statement or block conditionally. So we could also make another if statement, the next expression or the next statement, like this. This would also do the same thing. But you can see how we can chain those together now. Let's make it more clear. This would be the same thing. And as we can see here, we do get another block right here that clearly belongs to this if. So it's a little bit clearer to read, but you can imagine we can leave off this brackets here, and then we would have the same behavior still. And then this would never be able to be reached, so something went completely wrong. Like that. We can always couple instructions together inside of a block. We don't need to have an if before of that. And all this does is basically couples all these instructions inside of a block, so that block basically gets treated as one instruction. Basically, more or less. It's a little bit simplified, but it's more or less what it does. So of course we can also evaluate other things, not only Boolean variables, but other expressions that evaluate to Boolean values. For example, if 5 is greater than 4, or really anything that comes to mind. Maybe we do have a name and then starts with a D, DA. This would evaluate to true, and we can negate it with, if the name doesn't start with the letters DA, then it was wrong, and so on. So we can really get creative here. Then the next thing I would like to cover briefly are loops. There is a little bit more to this topic that I would like to go over in one of the next videos maybe. But we basically have two kind of loops, and these are for loops and while loops mainly. And a for loop is basically like this. It has 3 sections and then also a block or instruction that gets executed in that loop. The first section here is an initialization of a value. So mostly that's an int or a loop counter, let's say, and we initialize that usually with 0. Then afterwards we can check before we enter that loop for basically an if condition. So if the counter is smaller than 100, and then the last section is an instruction that gets executed after a loop. So for example, counter plus equals 1. So we start from 0. So we initialize the value first before the loop starts. At the first iteration, we initialize the value here with 0. Then we check if that value is smaller than 100, which it is. Then we execute this code right here. And afterwards, we jump into here. Then we check again, is that value still smaller than 100? And we execute that code. So this code would start with the first value of 0, and it would update the counter every loop with 1 until we reach the value 99. 99 is the last time we enter that loop here, because afterwards we exit out of here, add 1 again, then we check is the value still smaller than 100, then it would equal 100, wouldn't enter here anymore, and we would exit out of the loop and be here in the next line. Okay, I hope that makes sense. Of course, we can use the counter here and print it to the screen. So at that point, we maybe should execute our program. We just have one user input here, and yeah, that should be fine. So one user input, and then here's our loop. As we can see, 99 is the last value that gets printed. Oh, something went completely wrong. How did we get there? If not, so my name starts with, here we can see David, which starts with DA. So it was right. So we enter here, and wrong is true. So not wrong is true, is false, I mean. And then we enter into here, into the else case, and we print something went completely wrong. So that's what we expected. And also the loop seems to work as we expected also. I just noticed that I don't have a new line character here, which I would like to add. And the other loop that we have is a while loop. And this basically is like an if statement just executed in a loop. So while the condition here is true, then we execute our code here in a loop. And of course we need to sometime break out of that loop, so based on some condition or anything, I will just set is wrong to false after the first iteration. Also here we can also have do while loops, but they are rarely used, so I will also not cover them right now. Next concept I want to cover are functions. A usual function we can define here at main as a function, for example. It has a return type, but main is a little bit of a special function. So I want to write my own function here. It has a return type, for example int, or if we don't want to return anything, then we have the return type void. Then the function also has a name, for example function. And then it has a parameter list or arguments that we pass to that function. For example, we can pass in 2 numbers, and let's make this name more descriptive. And of course, now an integer return types makes more sense. And we can do some computation here. And afterwards we can return a value like that. And we can see here this expression here, which evaluates to another integer. And that integer will then automatically be returned. Of course, we specified multiply and not an addition, so we would do something like this. Then we would be able to create another integer result, and that would be equal to multiply. And then we have an a variable, and we also have a b variable. We have a b variable, but it's unsigned, so maybe we could use the c variable. As we can see here, the name doesn't matter. And we can also, of course, print out this result again. Like this. Of course, we also want to have functions that we just want to use in place and nowhere else. And an easy way to define functions as a variable or as an object is to define them as a lambda. We first have a capture. I won't dive into that right now. I will also cover that in a later video. And also the same as we had in the regular function, we have our parameter list or the arguments that we want to pass into that function. And then we can annotate the return type like so. And then we can have our logic inside of here. And we can also just return value here. And then we can, just as we did with the regular function, call our add function with a and c and also print the results to the screen. This notation might be a little bit intimidating, but I will ease into that a little bit. We can also automatically deduce the type that the function returns with the auto keyword. And as you can see, Visual Studio already suggests that we annotate the return type in this kind of lambda notation. And now we already are very close to the notation that we have down here, where we have auto as a return type, then our function name, and basically like that. Of course, auto is not the return type here, but the type of our function. So the next thing that I want to do is arrays and vectors. We already have used arrays. As we can see here, we have an array of 15 characters. An array is basically just a list, which is basically just a chunk of memory with a lot of variables with the same name in a row. So let's, for example, do an integer array. And we need to specify how many numbers that array should hold. So maybe 5. And then we could initialize them already with 1, 2, 3, 4, and 5. As we can see the slot here in which a number lies. So in the 0th slot, or the first slot, basically starting from 0, is the number 1. Then in slot 1 is number 2, slot 2 is and so on. And we could access those numbers with specifying our slot here. And we can also override them or do anything that we would like to do with variables usually. This is the old way of writing arrays. We also have a new array type in C++, which is the std array, where we can specify our type name and then the size that the array should hold, and we could also initialize them same way. And we would get more functionality without any downside, basically. As we can see, we have a lot more functionality exposed to us now. And we can also use all the standard algorithms on it. So you should really prefer to use the standard array now. And we also have this add. We have an overload for the bracket operator here, of course. More than array 2 equals to 5. That would also be possible. But you should usually prefer the add method that basically does the same thing, but it performs a bounce check. So if you, for example, enter 66 here, the IDE would warn you maybe, but in a more realistic scenario where this number would get filled in with dynamic data, the compiler can't help you, and C++ would happily access the memory at that place, and you would get a really hard to read error message maybe if you're lucky and the program crashes. If you're unlucky, nothing would happen and it would do completely wrong calculations. So this modern array offers you the add method, where you can also provide an index, but it would give you an easy to read error message where you see directly what went wrong. As you have noticed, an array is always a fixed size. So to mitigate that issue, we also have the vector, where you only specify a type and you can also initialize it with how many variables you want. And the cool thing about a vector is that you can append new values at the end of it and basically grow it dynamically. That's really cool. And to iterate over an array or vector that is a modern array, you can use this for each syntax. It basically steps through the loop for each element in the vector or array, and we can also of course print it out. And let's run this maybe again. And as we can see, we have our numbers here in the vector, and we have added a new number here at the end, and we can see that here. So the next topic I would like to cover are optionals, and we mainly use them for return types, especially in functions. We sometimes want to return something and sometimes not. An example of that would be an optional integer. Return if cool, maybe. Then we would like to A, else we would like to return a null option. Something like this. So we pass in an integer, we check if it's cool, and if it's cool we return it, and if it's not cool then we return nothing basically, or an empty optional. And then we can later on check if it was cool or not. So let's maybe save it. First return if cool. Let's pass in some number. And then we can check if there is something filled inside of it or not. This is a really dumb example, but I hope it gets the point across. And then we can get the value from the optional again. It's a really cool feature, but the example is a little bit not so good. But I hope you get the point. And we will also see some more practical examples of when to use it in later videos. I just wanted to introduce you to the topic right here. So let's run that, and we should see that it's a cool number, hopefully. And as you can see, the number so-and-so is cool. So the next topic I would like to introduce, I forgot to cover references earlier, so I will cover references now. And basically, if you have an int tuple, we initialize that with something, then we can have a reference to that value, and we annotate that with this symbol. And if we change tuple ref at any time, we will change the original value also, because this basically just is a reference here, so it is more or less like the original. It's basically like an alias. So if we run that, we can see the value of Zulu is now 8, even though we just assigned 8 to the Zulu reference. Are pointers and smart pointers. And that usually gets a lot of attention, and it's all mysterious and everything, but I really want to keep it very short and brief here, because it's not a too difficult topic in my opinion, and it's overhyped, I think. So a pointer to an integer we can just declare like this, and we can initialize it like that. This operator just means we get the address in memory of A, and pointer just means, okay, this stores the address of something, and that something is an integer and has the name pointer or ptr. That's already. And pointers are just optional references, and they are usually to prefer. Pointers you just want to use if you have an optional reference. But usually we don't want to concern ourselves with regular pointers too much at all. But let's see how we can get the value of A through the pointer now. And for that we just need to dereference the pointer. And we can do that with the star operator. So what's a little bit tricky about pointers is the notation, that we have a lot of stars and other special characters, but the concept itself is not too difficult in itself. These raw pointers in C++ should never be owning, so they should never be concerned with when to create or delete values. They should only really point to something or not point to something. So, but they should never hold ownership of something. This will become more clear maybe in following videos. If you need to have optional data that needs also to be able to hold ownership of something, then you should use unique pointer. And for that we need to include memory. It already suggests to do that for us, so I will just click on it. And we can create a smart pointer with make unique, and then we can call the constructor of this object. This is mainly used for bigger objects that we want to store on the heap rather than the stack, like this. And the smart pointer would already clean up after itself at the end of its lifetime. So in this case, when we reach this point here in main, then the smart pointer would clean up after itself before the operating system has the chance to do so. And of course, we can also access the value of the smart pointer in the same way, like this. Then the next topic I would like to cover are classes. Classes, structs, and objects. So, first of all, what are classes? Classes are basically blueprints that we can use to construct concrete objects, and objects are then just instances of that class. You can imagine really classes as blueprints for a house, and that house gets built multiple times. Then all of these houses follow the same blueprint and have the same features, but they are not the same. So to demonstrate that, we can create a house blueprint or class. This house can have public properties, for example, price or maybe height and, I don't know, number of doors. And privately, we would hold a copy of these things that get passed to us when we are constructing that house. And we can fill them in like so. Like so. This means the price that we have locally, this, gets initialized with the price that we pass in here. And the same applies for the height and the number of doors. And then we could also have some code that runs whenever we construct a house. So let's say maybe another new house, something like this. And then what functionality does a house have? I don't know, but it can print information maybe. This is a method of the house. A method basically just means it is a function inside of the house. So methods are basically just functions inside of a class or struct. The difference between struct and classes is very small in C++, at least functionality wise. The default, if we didn't specify public or private here, the default for house would be private and the default for struct would be public. Semantically, I try to differentiate the two. Classes are really more complex things that have custom functionality for me, and structs I try to use for anything that is purely data. We might see more examples of that in later videos also. And to print the info of the house, we can then also just print line again and then like that. And we can access all the variables, all the members of our class here. And with that, nothing happens. We just created a blueprint to create a house with that properties and behavior or functionality. To do that, we can create a house variable, my home, and then we can pass in the price, then a height, and then number of doors, let's say 50. And then we can use the functionality of that house, like so. And that is really the gist of it, and also leads into our next topic, which is inheritance. So we have defined the properties of a very basic home now, or a really basic house. And sometimes we want to extend that without changing how a basic home looks like. So we can define a new class. And this inherits from our house. That means we already got all the functionality from our house, and we can now add on to that. And the logic here is that when we construct our special home, we need to construct base first, and then we do our stuff. We could also take in more arguments here and set our special properties here for our special house. In fact, let's do that to demonstrate it. Yeah, maybe let's not save anything. Maybe we can just take in a multiplier. That would be funny. And all the properties that we have in here will just get multiplied by our mult. And just to see what happens, we'll also print special house was created. Something like this. And we can also extend the functionality of our house now. And a special home might also be able to jump. And it might also increase in value. And I would like to demonstrate here that we can still access the functionality and members of our base class. So we would need to change this from private to protected. Now we can access all of the members here, and we can increase the price by the amount. And then we can create our special home. Special house dot print information. Then our special house can also jump. And after jump, we can, of course, increase the value of the house, because that's pretty cool that it can actually jump. And after that, we can print the information again, and now the value should be higher. Now let's run it again. First, our value was 3000. Then the house jumped, and then afterwards, we increased the value by 1000, and then the value is 4000. What I would like to also show that we can override what the base class offers us. And as we can see here, we can only override virtual members. So we need to annotate this with a virtual keyword. And I think we need to specify our const first here, like that. And then we can do something special there. Like so. And as we can see now, our special functionality gets executed, and for the regular house, it just executes the regular thing. That comes in handy if we store house pointers, and this we can set to special house, or we can set it to our my home variable, and we could access both of those. This comes in handy if we would set it based on a condition. Let's demonstrate that. So we first have a house pointer, and if it's wrong, then house pointer is my home, and of course it needs to be the address of that, and else the house is the special house, like so. And then we could access the print info, and if it's a special house, it would execute the special info, and if it's a regular home, then it would just execute that. And we can see which one it takes by executing it again. And as we can see, we have indeed a special home saved here. So we can reverse that, and then it should use the normal home, like so, as you can see. Then what I would like to cover next are standard template library algorithms. We have already covered how to create a vector. Let's create another vector. Let's throw in some random numbers. As you can see, they are not ordered at all. And what algorithm allows us to do, which we should include first, gives us a way to use all the most common algorithms that we usually use on all the types that C++ offers us. And also we can make our custom types that work with all the algorithms. But I would just want to show you how they work. For example, we now have a sorting algorithm, and that basically only needs some things, which is the beginning iterator and the end iterator of that container, and it would happily sort it for us. So if we would print it again afterwards, then if you would run it again, then we would see that it has already sorted all the numbers for us, as we can see here. And there are many more algorithms that the algorithm header offers us. We will explore more of them in the following videos. In the meantime, you can just look up the algorithm header on C++ reference or CPP reference. Then I want to really quickly go over how error handling works with try and catch. Basically, we have a try block. If something goes wrong, we can throw something. In C++, we can throw anything. We could throw 4, 5, we can really throw anything, but what we usually want to use is runtime error, and we can give it a message, and we can catch everything that gets thrown here. We need to specify what we want to catch in here, and one of the most general exceptions that we can catch is an exception, and we want to catch it by reference. This basically is a way to treat exceptional cases where we can interrupt the regular program flow with a throw. We can do some stuff here, and then if something exceptional happens, we can throw an error and exit our regular execution and handle the exception here and do everything to clean up or exit the program cleanly. And also we need to specify what we want to catch here, matching this. So this needs to be convertible to here. And if it's not, then it would run into the next exception catch block. We could have multiple of this. And with 3 dots, we can have a catch all. But you should usually not use that. You should really specify what you expect. But if you want to catch everything, then we can just specify 3 dots. And have an exception block that catches everything, like so. So let's see if that works at all. And of course I've written that wrong, but it works. We have exited our regular program flow here and jumped into here and caught our exception. I just want to demonstrate something. So I really want to drive the point here home that we exit our execution here and do not execute this. As you can see, as soon as we hit this line, the execution here in this try block ends and we go straight into the error handling. So the next thing I want to cover is how auto works. We've used auto all the time. But auto basically just means that we deduce the type on the right automatically. And we can see string gets automatically deduced. But if we use 5, then it will become an integer and so on. With the Visual Studio Code plugin, it's really fun to play around with that. But I just wanted to show you how that works. And we could also have a reference, and that works as you would expect, like previously here also. Even though the value on the right is not a reference, we would then have a reference where the type is automatically deduced of that reference. And if you don't want to change the reference, we could also have const reference, like so. And that makes sense if we don't want to copy huge data types and just want to keep a reference to that original storage of the huge data type. For example, if we have textures in games, we don't want to copy them everywhere. We just want to have a reference to the original, but we don't necessarily want to copy it. Then also we did cover basic I/O, but we didn't cover how to write and read from files. So I will cover that now. We basically can write to files. with an output file stream, and let's call it sample.txt, and then we can just write to that file as we would use any regular stream. Test data. And then to make sure it gets saved to the file, we need to close the file. And then of course we can also read everything that we have saved to the file in again. Also the same path, sample.txt. And also here we can use that pretty intuitively, but there are some extra steps that we need to do here. We need a variable where we can store the file in, and then we can use getLine, and we need to specify where we want to get the next line from and where we want to store the next line, and then we can print it out. And then we can dump our line. Something like this. Let's run it. And as we can see, we have read our test data successfully. And we should also have our example.txt right here. As we can see, we have our test data in here also. Then let's cover some more STL containers. Next would be maps. Sometimes we want to map data with a key value relationship, and we do have a map for that. And let's use a string as the key type. And I want to map that into an integer, and let's call it hmap. And we can initialize that with key value pairs. The first one needs to be a string, for example David, and then 27, and then we could have Alice. I don't know how old Alice is, maybe pretty old. And then we could also have Bob, which might be 22. And of course we also need to include map here. And now we can read in something with a key. So let's define a key. Let's print out the key, which is the name. And then we can use that key to access the map and resolve it for the name, for the age, of course, like so. And as you can see, David is 27 years old, and that's correct. Another thing that might be useful are sets. Sets are just collections with unique data in it. So if you specify a set, then we can specify numbers here. Let's make sure we have some doubles. Of course, this needs to be std set. And also set needs to be included. So let's let Visual Studio Code do that for us. And if we would print our numbers now, you would maybe expect it to have 7 numbers in it, but it filters out all the duplicates automatically. So let's run this again. And as we can see, it only has 1, 2, 3, and 4. It's all the numbers that we have in here. So that's a pretty cool trick that we can use to get rid of duplicates in data sets. The next thing that I would like to cover are tuples. And they are basically a list of data that represent data point together. Let's give you an example. So we could use a tuple to represent a person, and that person might be named Charlie and might be 28 years old and might have a height of 5'9", like that. This would be an easy way to model data without having the effort to create a struct or class just to bundle these information together. So another thing that I would like to cover are function objects. And these are just objects that can be called. And what I mean by that, I will show you right now. So we just have a class or struct. And in here we need to specify the operator. This looks a little bit weird, but the operator name is this. This basically just means it can be called like a function call. and then we specify the arguments that this operator takes. An operator, by the way, is just a function, just that it gets called a little bit differently, like this. And then we can instantiate it, like so. And we can use it to square numbers, like this. Right now, just know that we can specify this operator, so we can call objects of that type, like a function. Also, what I want to cover is, we did cover auto, but maybe we want to have another way of type inference. And we can use decltype for that. And then we can use another variable here to create another variable of the same type. And this can be pretty useful sometimes. Then one thing I would like to show you is how to create a namespace to basically group custom functionality together. For that, we need to go here and create a namespace. Let's call this my namespace. And then we could create, for example, another multiplier. And that just makes sure that we don't get any confusion which multiplier we mean. So we can encapsulate them into namespaces. And let's do a really weird multiply here. But that just makes sure that we can now differentiate this multiply and this one, because they are in different scopes. And to call this now, we can use my namespace and then the namespace resolution operator, which is this. We've been using this all the time because the standard already groups all the functionality into the STD namespace, and then we can call my multiply with some values, like so. Then another thing that I would like to show are enumerations. So sometimes you don't want to have magic numbers, but something that represents the context or meaning that you really work with more. So you can have enumerations like this, and then you can create, instead of mentally assigning a color to a number, we can just have enumerations, and then we can create variables like so, and also do switch statements on these enumerations. So in case this is the color red, then we execute this code right here. And then we have a default case, like so, and we could copy this for each color to check for each color, or we can of course also do if statements. Because green is not a color, green is one, like so. So much for that. These can also be very useful. Maybe let's cut it here. We will go into more depth in the following videos. I just wanted to have a quick overview of the most important C++ features all in one video. I will see you in the next video.